Good morning friends, welcome to the series on networks, signals and systems. We expect all of you have already gone through the basic electrical engineering course where you have covered basic Ohm's law, Kirchhoff's current law, voltage law, network theorems and basics of single phase AC circuit, three phase circuits, impedances, complex impedances, phasors, etc. We also expect that you have been exposed to basics of integral and differential calculus and linear differential equations. We will study here in this subject the behavior of interconnected network elements, primarily the passive elements like resistance, inductance, capacitance, mutual inductance and so on, and their behavior, that is the variables, voltages, currents, charges etc. in different branches of a network, how they behave with the under the influence of different types of signals. So, we shall be considering on the one hand network behavior as it is and different types of signals, their influences on the network. We will also at the later stage go to general systems, general physical systems and try to find out how these equations, the network equations are applicable to general physical systems as well. We will also go through the graph theory that is extensively used in networks. Some elementary concepts of graph theory will also be introduced in this particular course. And after 2 or 3 lectures, we will go through kind of a tutorial exercise. We will discuss some typical problems and we will work out in this class. So, let us start with the elementary concepts which you have already probably gained in earlier classes. This will be only to augment your earlier informations with certain newer informations. See, there are 2 types of sources in electrical engineering, electrical energy. 2 types of sources, there can be a voltage source or a current source. Again, a voltage source can be an independent voltage source or a dependent voltage source. Similarly, a current source can be independent current source or a dependent current source. A voltage source is normally shown like this. A symbol for a voltage source is like this, symbol for a current source is like this. So, this is a voltage source, this is a current source. Now, in reality, no source is ideal. An ideal voltage source will have a voltage current characteristics like this, that is ideal one. The voltage remains constant for all values of current. As you keep on drawing more and more of current, in reality there will be more and more of internal drop. So, there is an internal resistance which we approximate to 0 provided this drop is very negligible. So, the actual slope, the actual characteristics will be drooping, the voltage will be dropping with the voltage with the current. So, this is the actual characteristics. Similarly, a current source will have a constant current and the voltage across the terminal will be varying. So, for a voltage source, for an ideal voltage source, a short circuit is an impossible event. You cannot have a voltage source which can be ideally shorted. If you have an ideal voltage source, it can never be shorted, because if you short circuit this, the terminal voltage becomes 0. A constant voltage source means terminal voltage should be constant. So, this is an impossible event. Similarly, a current source, an ideal current source which is supposed to supply a constant current, cannot be open circuited, because the current has to flow, it has to have a path. So, an ideal current source cannot be open circuited, open circuit condition is an impossibility. Similarly, short circuit condition for an ideal voltage source is also an impossibility. So, this is current source, this is impossible, this is also impossible for a voltage source. Then we have dependent source. Dependent sources can be 4 types. You can have current controlled voltage source, we call it CCVS, current controlled voltage source. So, we will have a symbol like this. This voltage for this kth source is proportional to some current through some other branch, that is Ij is the current through some jth element in the network multiplied by some alpha. So, this is the terminal voltage. So, this is CCVS. Similarly, you have CCCS, current controlled current source, shown like this, and IKT will be some A times IJT. So, this is current controlled current source. Similarly, you have voltage controlled voltage source, which is VKT equal to beta times VJT, and voltage controlled current source VCCS, which will be shown like this, IKT equal to some B times VJT, this is VJT. Okay. So, these are the 4 different types of dependent sources. Let us have a small numerical problem. Suppose you are given a voltage source Vs connected to a resistance R1, and you are having a controlled source VCVS whose voltage is 0.1 times Vc, and you are having another source, a current source, dependent current source CCCS, sending a current through resistance R2. The voltage across R2 is Vc. Note the signs of the voltages and the currents. This is I2, this is I1. Now, you are asked if Vc is equal to minus 10 volts and I1 is equal to 3 amperes, what would be the values of I2 that is flowing through R2 and the voltage of the VCVS, that is what is this voltage V. Now, you can see this resistance value 50 times I1, R1 is given as well 50 times I1 is equal to I2. This is given as 50 I1. So, 50 times I1 is equal to 50 into 3 amperes, that is 150. This will be equal to I2. Is that all right? Because this is a current source that is sending a current through this, and the current source is a dependent current source 50 times I1. So, whatever be that value of I1 is given as 3 ampere. So, that multiplied by 50 is the current I2. So, that comes to 150 amperes. Okay. Therefore, voltage V of this VCVS will be 0.1 into Vc, that is minus 1 volt, R2 was given as, see, Vc is equal to minus 10 volts already given. So, 0.1 times Vc, so that gives you minus 1 volt. Okay. If you are also asked to calculate R2, how much will be R2? Now, you know Vc, that is given, and you are given I2. So, you can calculate R2 will be 10 volts divided by 150, so many ohms, that is 1 by 15 ohms. So, you could be given any number of parameters to be determined for a control source like this. You can calculate like this. Now, we come to series and parallel connections, of sources, series and parallel connections. Now, let us see when can you have series connection of sources like this, voltage sources. You can put them in series connection of voltage sources. What you will get? You can have V1, V2, V3, V4 up to Vn connected in the same sense. So, this is Vt. Therefore, Vt will be summation of all these voltages Vit, I varying from 1 to n. Parallel connection of ideal voltage sources is not defined. parallel connections of ideal voltage sources it is just not possible. It is just not possible to have parallel connection of ideal voltage sources. For example, if you have V1 and V2, two different voltage sources, if you put them together, what will be the terminal voltage? It is undefined. Okay. You can connect ideal voltage sources in parallel only when they are having identical voltages. All right. So, cannot be defined except in situations where they are all identical. They are all identical. Similarly, parallel connections of current sources, parallel connections of ideal current sources. You can have I1, I2 and so on, IN. The net current IT will be I1T plus I2T and so on. So, current sources, if they are put in parallel, will give rise to an equivalent source which will be equal to I1 plus I2 plus I3 and so on. Like the voltage sources, the current sources cannot be put in series unless they are all identical. That is, current sources, if you want to put them in series, all of them must have the same current rating. So, I1T, I2T and so on, INT. This is equivalent to let us put the symbols IT, where IT is equal to I1T equal to I2T and so on. In the previous case also, for voltage sources, parallel connections, if we put, all of them will be of the same voltage level. So, if V1, V2, V3 and so on are to be put in parallel, then Vt equal to V1T equal to V2T and so on. And I am not always writing V1T, V2T, the argument is dropped, it is understood. This means V1T, V2T, V3T and so on. It may be constant, it may be varying with time, but they must be identical. So, this is all about series and parallel connections of current sources and voltage sources. There is another situation when suppose you are having a voltage source in parallel with a current source. What will be the equivalent? Yes, I am expecting a question. Can you tell me what could be the equivalent of this? This is Vt, this is It, both are ideal sources. Now, the terminal voltage must be constant. So, this is equivalent to just the voltage source Vt. So, current source is redundant here. current source does not have any role to play, it does not give any additional voltage, all right, because the terminal voltage must be same. Okay. So, for a parallel connection of voltage source and current source, we can replace this by an equivalent single voltage source of the same magnitude Vt. Similarly, if you are having a current source in series with a voltage source and current source in series, what will be the equivalent? It will be a current source, because the same current has to flow through this. So, voltage source becomes redundant, all right. There is no influence of the voltage source here as such. Let us work out a simple example of a network connection with the sources as indicated here. Suppose you have a 2 ampere current source and 2 volts voltage source connected in this fashion. This is given as 4 ohms, this is 3 ohms, and the polarity is shown like this. What will be this current I y, I z, and if I denote this as I x, I x is 2 ampere given, and V x as the voltage across this. If I denote V x as the voltage across this, so question asked is how much will be V x, I y and I z. Also, what will be the power supplied by the 2 sources. Now, you can see 2 ampere current is flowing from this side to this side. So, this is at a higher potential, this is at a lower potential. Current is going like this. So, 3 ohms into 2 amperes, 6 volts will be the drop across this from this side to this side. So, the polarity shown here, if that represents Vx, so Vx will be minus 6 volts. Is that all right? Minus 6 volts. Now, how much will be Iy? Could you please tell me what will be Iy? Iy, you can see 2 volts will be appearing across this. So, it will be 2 volts divided by resistance is 4 ohms, all right. I will not put volts and ohms, we can straight away write 2 by 4 amperes, that is 0.5 ampere. Is that all right? Now, what will be Iz? What will be this current? This is 2 ampere, this is 0.5 ampere. So, 1.5 ampere current will be flowing through this in this direction. So, Iz will be minus 1.5 ampere. Is that all right? How much is the power supplied by the current source? How much is the power supplied by the current source? Now, you have seen that this is getting charged. This voltage source is not supplying power, it is receiving power because the current is flowing in this direction. So, voltage source is receiving a current of minus 1.5 ampere, that is 1.5 ampere in this direction against a voltage of 2 volts. So, voltage multiplied by current 2 into 1.5, 3 watts of power will be received by the voltage source. So, power received by the voltage source, I write received is 2 into 1.5 watts, that is equal to 3 watts. Okay. How much is the power consumed by this? How much is the current Iy? 0.5. So, 0.5 4 into 0.5 squared is the power consumed here. Then 2 amperes into 2 squared into 3, that much power, 3 into 2 squared, that much power is consumed by this, and the power received by the voltage source is 3 watts. So, the total power will be supplied by the current source. So, that works out to be, this is half squared 1 watt, this is 4 into 3, is it not? 12 plus 3 plus 1. So, that gives me 16 watts. So, 16 watts of power will be supplied by the current source. Okay. Let us now consider a simple network where we can use this principle of parallel connections of voltage sources and current sources. All right. So, we have a network, I will just draw this. This is branch 1, this is branch 2, this is branch 3, and so on. Okay. They are all connected to a network like this. I am showing only the part of the network that is of relevance at this moment from this side. Rest of the network is shown like this block. Now, this can be equivalently represented as if I am connecting all these branches separately by different voltage sources of the same magnitude. It is possible. This is branch 3, this is branch 2, this is branch 1. All these are connected to the same network segment. So, what we have done is replacing a single voltage source, we have replaced the single voltage source by multiple sources of the same magnitude Vt. This is also Vt, this is also Vt. At times it simplifies our computation. Let us see one simple example. Mind you, it is not necessary that all these network problems can be solved by a unique method. You can always adopt any method for solutions, but at times certain methods will be having more advantages over other methods, and for that we have to reduce the network conveniently at different times using these principles. So, let us have a network like this. We are required to calculate the output voltage V0 for this network. This is a 10 volt source, and we have got all these values. Okay, we will be giving the values soon. This can be reduced. First of all, let me draw this. R1, R2, R4, R5. Okay. Suppose we are given all these resistance values as 1 ohm, R1 equal to R2 equal to R3 equal to R4 equal to R5 equal to 1 ohm. It is only a simple example that we want to show you. You can have any values, but the reduction is very clear. Now, this is a 10 volt source, this is a 10 volt source. Now, a voltage source with a series resistance, as you know, can be replaced by a current source with a parallel resistance. This is what you have done in Thevenin's equivalent conversion from Thevenin to Norton equivalent. So, 10 volts by 1 ohm, that gives me 10 ampere current source in parallel with a 1 ohm resistance. Again 10 volts by 1 ohm, this source will also be 10 ampere with 1 ohm. Okay. And then you are having let me redraw it. Let me redraw this, because here there is a connecting resistance in between. So, this terminal and this terminal cannot be directly connected. So, let me draw the equivalent from here. Ten ampere, 1 ohm, we can put it this way, then 1 ohm, 1 ohm, this is R5, this is R2, R4, R5, and you are having another source 10 ampere with 1 ohm, and this is, see, this is connected at the output terminal with R5. So, this is connected here. Okay. This is the voltage that you are interested in, okay, V0t. Okay. So, 1 ohm and 1 ohm in parallel can be replaced by, this is 10, this is 1 and 1 in parallel will be 0.5, that is good, 0.5 ohm, then you have 1 ohm, then this and this you can see. Okay. If we, can we put them together? Should I put them together? Okay, we will retain it as it is, because this is the output terminal we are interested in. So, we will keep this as it is. Let us reduce this network. So, 1 and 1 has been reduced to 0.5, 1 ohm, then 1 ohm, and this side is retained as it is. Now, 10 and 0.5, 10 ampere and 0.5 can again replaced by an equivalent voltage source of 5 volts in series with 0.5 ohm. 0.5 ohm, and then you have 1 ohm, and then this side you have 1 and 10 ampere. Okay. So, we have used the principle of separating the voltage source into two equivalent voltage sources, then voltage source is replaced by an equivalent current source, and then we are making reductions in the network elements, parallel elements replaced by a single one, then again from current source switching back to voltage source, then you are having two series resistances, put them together 1.5. So, I can put this as a single current source. What will be the value? So, from here, okay, I will draw in this side from 5 volts and 1.5 ohm, I can draw a resistance of 1.5, 5 by 1.5, yes.
So, there is a 1 ohm resistance in the parallel branch.
1 ohm resistance in the parallel branch.
That means, sir, in the current source 10.
Yes, yes. There is a, thank you very much, there is a 1 ohm resistance, I forgot to show that. So, 1 and 1.5, 1 and 0.5, that makes it 1.5, and this current source will be 5 by 1.5. So, 10 by 3 amperes, and then there is a parallel resistance of 1 ohm, and then you have 1 ohm, 10 ampere. Okay. So, from here you can see 1.5, 1 ohm and again 1 ohm. So, what will be the net value? 1 ohm and 1 ohm is 0.5, with that 1.5 in parallel. So, that gives me 0.375. Now, you see I have put all of them together. So, this node, so far I did not disturb this node, which was representative of that earlier node here, that is, this represents the voltage V naught. Okay. So, that has not been disturbed, that has not been disturbed here. Okay. I have just replaced this voltage source, but I have not replaced R5 so far. So, the voltage across R5, this is same as the voltage in this entire combination now. So, how much is this? So, 10 by 3 and 10, two sources together will be 13.33, this is 3.33 plus 10. So, 13.33 amperes in series with 1, 1 and 1.5. So, that gives me 0.375, sorry, this will be parallel, 0.375. And what is this voltage? Voltage across this. So, it is the current multiplied by this resistance. So, the voltage V naught will be 0.375 into 13.33 volts. Is that all right? You could have solved it by any other method, nodal analysis and many other methods. This is only to demonstrate the use of that principle of dividing the voltage source into two equivalent identical voltage sources and then addition of current sources and so on. We will take up some problems using this principle to determine the voltages under different situations when R1, R2, R3, R4 are having different values. So, I will take that up in a tutorial class later on.
Sir,
yes, please, please.
Sir, we have demonstrated the use of the dividing voltages in this problem.
Yes.
And we can solve this problem by the network analysis method also.
You can solve this by any other network analysis
so
techniques.
Specific advantage of this method,
we do not demonstrate at this moment specific advantage. Advantages will be clear. See, no particular problem is having a unique solution as such, but there are certain shortcuts which you will find in course of time when you attack a particular typical network problem. Okay. So, you should be always conversant with the conversion of one type of source to another type of source, or dividing the voltage source, or sometimes the current sources. If there is a single current source, I can always break it up into many current sources in series, identical current sources in series. Similarly, for voltage sources, one single voltage source, I can always split up into equivalent identical voltage sources, as we have demonstrated here. So, I will just mention the principle for a current source. Similarly, if you are having a single current source feeding a network like this, and there are elements like this, say this is the rest of the network. This can be equivalently shown like a current source here, a current source here. That is, I am having multiple current sources. This is element A, B, C, it can be a general impedance. So, A, B, C, and this is the rest of the network. I can show it like this. You can see this same IT, 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 and so on. The same current source has been split up into 3 identical current sources in series. It is possible, all right. This is an interconnection that I have put. It was not there earlier. How much is the current through this? I can assume a current IT coming like this and another current IT going like this. So, IT this way and IT this way, that will be cancelling. So, there is no current. So, it is a virtual connection. It is a virtual connection that I can make with 3 current sources. Okay. So, we can demonstrate this principle of splitting up a single current source into a number of series current sources through a simple example. Let us have a current source. Once again, I will take a very simple network with simple values only to demonstrate the principle. R1, R2, R4, R3, R5 and R6. You are required to calculate the current I0 through R6. Okay. Let us mark this particular point as A. Okay. This is a 5 ampere current source, all right, 5 ampere current source. We are having all the resistor values as unity. One ohm. So, this source you are asked to calculate I naught. This source can be replaced by 2 equivalent current sources as in this diagram. This is 5 ampere, again this is 5 ampere. Okay. Now, I am putting 1 ohm 1 ohm, 1 ohm, 1 ohm, 1, 1, okay. And you are asked to calculate the current through this. So, this can be again, see this particular network, now I am going to, this is point A, mind you, I am going to replace by a voltage source this element. 5 ampere with 1 ohm will be 5 volts with 1 ohm in series, very good. And then you are having 1 ohm, this and this, I will show them separately, okay. And then this 1 ohm, similarly this side you have 5 volts in series with 1 ohm, okay. One ohm, all right. This is the polarity. So, let us further reduce this. This point A comes here, all right. This is the point A, because this is replaced by this, okay. So, this is a point A. Similarly, this is replaced by this. So, this is the junction, okay. Now, this point A this is 1 ohm, from this point this is 1 ohm, this is 5 volts with 3 ohms resistances. So, I can replace it again by a current source. So, I will replace it by a current source and resistance. How much is that resistance? This is 5 by 3 ampere and 3 ohms, okay. And then this is the point A, we are having 1 ohm, 5 volts, and then 1 ohm. So, 3 and 1 ohm in parallel will be 3 by 4 ohms multiplied by 5 by 3. So, this combination I can replace by now you see I am replacing once again the current source by a voltage source. So, it will be a voltage source, polarity will be, because the current is going like this. So, this is at a higher potential. So, it will be like this. So, 5 by 3 is the current source value multiplied by the equivalent resistance 3 by 4. So, it will be 5 by 4 volts in series with 3 by 4 ohms, okay. And then you are having 1 ohm. So, how much is the current now? I naught. So, I naught will be 5 volts plus 5 by 4, 25 by 4, correct me if I am wrong, 5 volts plus 5 by 4 divided by the total resistance 1, 1, 2 plus 3 by 4. So, 25 by 11 ampere. Is that all right? You could have obtained by any other method. We will take up similar problems in the tutorial class with different values of R1, R2, R3 for this problem also. Now, we shall be discussing something about we shall be discussing something about network elements. The network elements are either passive or active. What are passive elements? What do you mean by passive elements? Elements which are not dependent on any energy source, like a resistance, capacitance, inductance or transformers. These are passive elements, okay. And active elements are dependent on some other energy sources, okay, like transistors. You require a DC supply, transistors, GICs, general impedance converter, negative impedance converter, FDNR, frequency dependent negative resistance. So, these are the examples of active elements: transistors, GICs, negative impedance converter, FDNR, frequency dependent negative resistance, and so on. Op amps. And passive elements are simple: resistance, inductance, capacitance and transformers. Where mutual coupling is also involved. So, these are the different network elements. We shall be concentrating mostly on networks consisting of passive elements, and very occasionally we will be mentioning about active elements. Then network elements can be linear or nonlinear. Linear or nonlinear. What do you mean by linear elements? What do you mean by linear elements? Linear elements obey the principle of superposition. That is good. So, we will be in the next class we will be discussing in details about the linearity and nonlinearity that exist in common items like R, L, C and so on, and what are the different types of nonlinearities that you come across in systems. Thank you very much. Good morning friends. We will continue with our earlier discussions on linearity of systems. As we had mentioned, a linear system will have the property like this. Mathematically we can write the property like this: if we excite a system by an input x1t, it can be either a voltage or a current, and the corresponding output is y1t. Similarly, if we excite it by an input x2t and the corresponding output is y2t, then any combination of x1 and x2, say a1 x1 plus a2 x2t, will result into a1 y1t plus a2 y2t if the system is linear. This is the principle of superposition. Now, sometimes you are given the system equation in the form of differential equations. How do you determine whether a differential equation is a linear differential equation or not? Suppose you are given, I will give you a simple example, say d square x by dt squared plus 2 into dx by dt minus 3 into x is equal to some forcing function f1t, maybe sin t, sin 4t. Another equation, d square x by dt squared whole squared plus 2 into dx by dt minus 3x is equal to sin 4t. The third equation is dx by dt, sorry, d square x by dt into t plus 2 into dx by dt minus 3x is equal to sin 4t. D square x by dt square plus 2 into x into dx by dt minus 3x is equal to 4t. Now, out of these, which one will be linear, which one will be non-linear, which one will be representing a non-linear system? Yes, well, of considerable value. So it will be somewhere in between. If R1 is 0 and R2 is 0, if R1 is 0 and R2 is 0, what happens? That is, across an inductance, if I switch on a supply as a DC voltage, if I apply across an inductance, pure inductance, there is no resistance, what happens to the current? It is L di by dt, which is constant, V. So, if it is L di by dt, which is constant, that means I will be constantly increasing. It is integral V dt. Okay, it is proportional to integral V dt. So, I will be constantly increasing. That means you will get a current that will be continuously increasing, and that will cause a secondary current also in the reverse direction, that will also be constantly increasing. So, both primary and secondary currents will be increasing continuously. Okay. So, this is a very interesting situation. For example, sometimes when you apply a sudden change in the voltage, say an impulse, pulse voltage, in a pulse transformer you get sudden changes, and then though the voltage is there is no change, alright, there is no change. So, on the secondary side there is no output. Whenever there is a change, there is an output on the secondary side. So, this principle is used in a pulse transformer. Okay, thank you very much. We will continue with this in the next class.